Okay, so we're going to be looking at problem number 739. And I already gave you some time to draw the kinematic diagram, but I want to look at the problem statement so we know what we're going to be doing here. So it says at this instant when theta is 90. So you'll notice that theta here is up by, this is the motor and this is the crank. It wants this angle to be 90 degrees from vertical. So we're going to put it at, if you would, 180 degrees from, kind of standard orientation. So we're going to move this so it's down, okay? And we're going to draw the kinematic diagram in that placement of the crank. And it says here that at this instant, it's rotating counterclockwise at 150 RPMs. That's the crank. And it's accelerating at 200 radians per second squared. So that means it's speeding up at that rate. Says use the relative acceleration method to graphically determine the angular velocity and angular acceleration of the nozzle, which is out here. So I drew our kinematic diagram in AutoCAD, so you had the chance to do that. So this is what my kinematic diagram looks like with that crank at that 90-degree angle from vertical, okay? And then what I did was underneath our camera, I've got kind of the process started, if you would. So for this problem, we're given the angular velocity of that crank at 100 RPMs. And I'll put on here counterclockwise, okay? And then the angular acceleration, that's this symbol, it's that little like alpha. Angular acceleration of that same link, number 2, is 200 radians per second, and it's accelerating. So that means it's also going to be going in a clockwise direction, in the same direction as motion. They want us to find the angular velocity of link number 4, the nozzle, and the angular acceleration of that nozzle. So I kind of have my givens and my things that I need to find. So first step is kinematic diagram, which needs to be done on AutoCAD. I added a sketch here just so that I can kind of draw on this as we're, kind of figuring things out. And it's also good practice. I do want you to always do, and I think I've mentioned this before, but I forgot it on the last example. Make sure you add your mobility equation to verify that you have the appropriate labels for your links and your joints. Because if something comes out other than one, that means you may have missed something or you've got a couple extras. So, so make sure that you do that mobility equation to be sure that you get one. This is a standard 4-bar mechanism. So where the motor is mounted, that's going to be the frame. Then our crank is going to be link number 2, the connecting rod, number 3, and then the nozzle is going to be link number 4. Okay. And again, this is just a sketch of. Our given is we know that we're rotating in a counterclockwise direction, 150 RPMs. We're accelerating, so our alpha 2 will be in that same direction. And then we're needing to find those two values, okay? Now, we are going to use that relative acceleration, but it requires us to use and to determine what the velocities are. Now, because we need to find W4, or the angular velocity of link number 4, if we go back to our equation sheet, to calculate for an angular velocity, we need to know a straight line velocity on that link divided by its distance away from its center of rotation. So here, if we want to find our W4, that means we need a velocity along this link, which is going to be velocity C, okay? So we have to find the velocity of C. Now, it appears it's going to be going in a counterclockwise direction. So that velocity of C is going to be perpendicular, okay, along this line of action. That's going to be our velocity C. We don't know its full magnitude, but we know its line of action is going to be perpendicular, right? So, so we're going to have to find that. So down here in our relative velocity equation, our unknown variable is first. So this is going to be the velocity of C. Now the velocity of C is dependent on our driver up here, okay? And our driver up here, the crank that's attached to the motor, we know is going at an angular velocity of 150. And we know that it is this length is 3 inches long. Okay, so we know the distance of that. So we can calculate the magnitude of point B, velocity of B, which is going to be perpendicular also to its radius of rotation, and this is going to be the direction of the velocity of B. That's going to be a known quantity. We'll calculate that in a little bit. So this is going to be our B right there. And then our velocity of C relative to B will be the last one that we put here. Yes, Christian. My knowns and unknowns. Yeah. Okay. So that means that when we do our velocity of C relative to B, it's going to be on a line of action that's going to be perpendicular to the line connecting C and B, or link number 3. Now, as we saw in our previous example, we need to find these in order to get our W, but more importantly, we need to find these for our next step, these accelerations. But let's go ahead and determine our velocities here. So our velocity of B magnitude-wise is going to be equal to W2 times the radius of rotation to point B. Okay. We know W2 is 150 RPMs, but we can't use that in that equation. So we need to convert our 150 RPMs to radians per second. So I'll do that on the side over here. I'm going to take my 150 revolutions per minute, and I'm going to convert that to radians per second. Make sure you always show the ratio method canceled out. So our W2 is going to be equal to confirm. I got 15.7075. So 17.71 radians per second. Anybody else get that number? Yeah, Lex says yes. Okay. So this is going to be the value then that we're going to use in this equation. So this is going to be equal to 15.71 radians per second. Let's do this to myself. And it's going to be multiplied by 3 inches. Okay. So I get 47.12. That's going to be inches per second is equal to our velocity at B. Okay, that's its magnitude. Anybody else get that same value or very close to it? Okay. All right, now that we know the magnitude of our velocity of B, that means that we know its magnitude and we know its direction is going to be perpendicular to link number 2, right, in the direction of rotation. So we know both magnitude and direction here. We don't know the magnitude for C relative to B, but we do know that its direction is going to be perpendicular to link number 3. Okay. And then if we go back over and we look at velocity of C, we know the direction of C, but we don't know its magnitude. So here we don't know magnitude, but we do know direction. So again, we've got 2 unknowns separated by the equal sign. We can do our vector equation and draw it to scale. So since we have 47.17, and if we look back, our distances were like 3 inches, 10 inches, 6 inches. I am going to actually draw this to a scale of 1/10. So I'm going to actually draw it at 4.712 is going to be the length of my vector so that it's reasonable with the kinematic diagram that I have here. So what I'm going to do first is I'm going to show the velocity of B in place. I'm going to change to a different object line. Since this is a horizontal line because it's 90 degrees from vertical, then it's pretty easy to know that my velocity vector then is going to be vertical. Okay, going straight down. And that distance is going to be the 4.712. Okay, so it's 47.12, but I'm going to draw it 4.712. Okay, move my number 3 out of the way. here. I'll put my arrowhead. This is going down because this is rotating in a counterclockwise direction. And then this would be representative of my velocity B, okay? So that's my first vector, and I'll copy this over in a little bit. I'm just kind of putting them on our diagram so we get the orientations correct. Then I'm going to change to object 3, and I'm going to draw a line out here, random, and it's going to be perpendicular to link number 3, okay? And this is going to be the line of action for the velocity of C relative to B, okay? And then my last line of action is going to be the velocity of C. Change that, align, and that is going to be perpendicular to link number 4, and I'm going to put it, going to move it over here, endpoint there. And then this is going to be the velocity of C. Now, I don't know if it's pointing in that direction, so I'm not going to put an arrowhead on this. This is just line of action. Okay. All right. So make sure on your kinematic diagram that you add those lines of action or those directions and or, actual velocities, like velocity of B. Any questions here? Okay. Now, over here on the right-hand side, I've kind of created, I did my vector equation. Velocity of C is going to be equal to the velocity of B plus vectorially C relative to B. Make sure that's by your vector diagram. And I added an origin here. So I'm going to copy these vectors, and I'm going to start with the velocity of B. I know that my velocity of B is going to be going straight down. It's going to be the first vector that I do. It's what I know the most about. I know magnitude and direction, so that's going to be my first one. Now I'm going to add to that the velocity of C relative to B. So I know direction only, so on the tip of vector B, I am going to copy over the direction of this vector. I'm just putting it at the endpoint. I really don't know which way it's going. And I'm going to represent that down there. Okay, that's just the line of action. You could show it going, the opposite way as well. Now I have everything in place on my right-hand side of my equal sign. So I'm going to go back over and I'm going to solve for the velocity of C. So the direction of the velocity of C is here. So I'm going to copy this. And I'm going to start it at the origin, okay? It's got some overlapping going on here, so I got to move my call out for the velocity of C. And then I'm going to trim the parts that I don't need. This one over here. My callouts could probably be smaller, but that's okay. Okay. So that is going to be the trimming off. I got my intersection right here. So now I'm going to add the arrowheads for velocity of C. Its tail is going to start at the origin and its tip is going to go to the intersection. So I'm going to go here and here. And then the velocity of C relative to B is added to the endpoint of B. So its tail is going to start at the tip of B and its tip is going to go to the intersection. So that one's going to go here. Okay. So very big. Now, I do need to add my dimensions. So I'm going to add a line dimension for C. Okay. And right now, it's probably appropriate. I'm going to make it a little bit bigger. I'm going to go into my dimension style manager, modify, fit, and I'm going to go 2 for this. I'm going to make it 2 times as big. Set as current and close. So it's a little bit bigger. And then I'm going to do my measuring of C relative to B because I know I don't need it for this, but I will need it for the acceleration. And then I could dimension my B, might as well add it. It's going to be that one. So I'm going to write down each one of these velocities, but I'm going to convert it back to the value it's supposed to be. So for instance, VB is 47.12 inches per second. Velocity of C relative to B is 16.682. It's going to do 16.68 inches per second. And then the velocity of C is 48.17 inches per second. Do you guys get similar numbers or same? Hopefully. Anybody else? I just want to confirm because I measured mine. Did you guys get the same values? Make sure that your velocity of C is perpendicular to the link. Okay. I'm going to do a quick save here. And I'm going to pause because I'm going to check my values because it doesn't mean that mine aren't correct. Okay, so my values are confirmed. And so by scaling these or moving the decimal place one place back to the right, then our velocities for B, C relative to B, and C are as follows. Okay. So now we're ready to move to solving for the angular velocity of link number 3. Because we have the velocity of C on the endpoint of that link, W4 is going to be equal to, and if we go back at the very top here, the velocity equation, the angular velocity is equal to straight line velocity divided by the radius. So that means on link number 4, we're going to use that velocity of C divided by its radius back to its center of rotation. So that's going to be the radius to C as well. We're going to use the value up here. Make sure it's the actual value rather than the scaled value. So 48.17 inches per second divided by the radius. So the length of that length is 6 inches. So these cancel out. And our W4 then is going to be 48.17 divided by 6. So you should get 8.028 radians per second because the inches cancel our top. And so we have nothing per second. So radians magically appear. We do not leave angular velocities in radians per second. So we are going to go ahead and we are going to convert this to revolutions per minute. And this is a final answer. So we want to put a box around it. And as we look here, we also have to add direction. Okay. So we need to know, is this going clockwise or counterclockwise? And if we go back to our diagram here, the velocity vector C is going down and to the right. So that means that this is going to go, I'm sorry, down and to the left. So that means that this is going to rotate in a counterclockwise direction. Make sense? So then I'm going to go back over here and we would want to put on here counterclockwise. Okay. So I want to make sure everybody get 76.664 RPMs. Okay. Awesome. So that's the first half. We've done the first part. Now we're going to do is we're going to use this information and we're now going to do the acceleration part. Okay. Now, if we look back at our diagram, you're going to notice that each one of our links here rotates either about a fixed center, link 2 and link 4, or it's kind of oblong rotating out in space and doesn't have a fixed center, which is link number 3. So that means each one of these links is going to have a tangential and a normal component. Okay. So let's kind of look at that and let's look at the acceleration now. So this is our third step. Feels like a lot more steps, but this is our third step. This is going to be the relative acceleration. Okay. So we're going to use as our template this very same format right here. The velocity is, or I'm sorry, the acceleration of C is going to be equal to the acceleration of B plus factorially the acceleration of C relative to B. So acceleration of C is going to be equal to the acceleration of B plus factorially C relative to B. And these are all vector quantities. And as we just stated, each one of these is moving around a fixed center. So each one is going to have a normal and a tangential component. So we're going to expand this out where we have the acceleration normal at C plus factorially the tangential acceleration at C. It's going to be equal to the normal at B plus factorially the tangential at B plus factorially the acceleration normal at C relative to B plus factorially the tangential at C relative to B. All right. So then now we need to determine what we know and what we don't know. Okay. For all of these, we know directions. Okay. We do know directions for all of these because it's either going to be along the line, maybe from the point to its center of rotation, or it's going to be perpendicular to that. So we can, if you wanted to, you could kind of add the second check mark for each and every one of these. It's the magnitudes that we're not going to be able to, we may or may not be able to figure out. Okay. So let's start with the normal component at C. We look at the options for calculating the normal component at C. We do know that C is on link number 4, and we do know the angular velocity, the angular velocity of link number 4. So we could use this first equation. We also know the velocity at C, the straight line velocity. So actually we could use the second one as well. So whichever one you want to use, we know that we can calculate the magnitude for that normal component at C. Okay. Let's look at the tangential. The tangential, notice that it's the radius times the angular acceleration. We do know the radius, we know the distance from the center of rotation, point D, out to C, but we don't know the angular acceleration. So this one, we won't know its magnitude. We will know direction though, okay? Normal at B. B is our known, that is our crank, B is our crank. So normal, we do know the angular velocity of that link and its center and its distance from the center of rotation. We also know VB and its distance. So definitely can find the magnitude there. And then the tangential, we need radius and angular acceleration. We were given the angular acceleration for this problem. So this is link number 2. So we know that the angular acceleration of link number 2 is 200 radians per second squared. So this one, we can also calculate the magnitude. Normal C relative to B. So we go back here. We have these two options. Now, we don't know the angular velocity of link number 3 because we're on that relative link now. So that's going to be the link that connects points C and B, which is link number 3. We don't know the W3, but we do know the velocity of C relative to B, right? And we know the length of that link. So we can calculate the normal there as well, the magnitude. And then as we look at the magnitude of the tangential, going back here, we know how long that link is. We know the radius for the for that link, but we don't know the angular acceleration for that link. So that one will have an unknown magnitude. So again, it worked out that we have two unknowns, magnitude of the tangentials of these two, okay? And they're separated by the equal sign. So the format that we have here, we don't have to move around. So now, before we start creating our vector diagram for this, let's go ahead and calculate the 4 known magnitudes or the 4 calculatable magnitudes for each one of these. And I'm going to start with the acceleration normal of C. So the acceleration normal of C, I'm going to go back over here. I can use either one of these equations. So just because W2 or W squared times the radius is first, I'm going to use that one. So this is going to be the angular velocity of link number 4, and we're going to square that times the radius to point C. So we know that W4 right up here is this value, but remember in this equation, we have to use the radians per second. So 8.028. Radians per second times the distance that C is from the center of rotation. That's going to be 6 inches. And so that's the dimension from here to here. 6 inches. So my normal component at C, what do we get? Oh, that's not right. What did I do wrong? Yes, we have to square that value. Yes, 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 yes. Oh, see, I was testing you guys. So easy to forget. You know, what's funny. So last year I did this very same lecture. Last year I did this very same lecture and I did that very same thing at the same place. Exactly the same. All right, so 386.69. Does that sound better? Inches per second squared. Yeah. Yeah, don't forget to square that value. Otherwise, yep, your answer is going to be very different. So if you end up with not right answers, make sure you did your squares where you were supposed to. It's so easy to forget. So I'm just going to put a line in right there. So that's my first magnitude. So we've got that confirmed. Now we're going to do our next magnitude, our next normal, the acceleration normal at B. Got line there. That's going to be equal to, and just for the heck of it, I'm going to use the velocity squared over the radius just because it's the other one. Velocity at B, don't forget to square it over the radius to B. So my value for my velocity at B, 47.12. And that's going to be inches per second. Make sure you put your units in there and square it. Divided by a radius of 3 inches. So my normal acceleration at B, $740.1 inches per second squared. Anybody get that same answer? James, you did? Okay, awesome. Thank you. All right. Then now, let's see. Need a new piece of paper here. Hold on. Put it on the paper. Maybe I did. These problems take a lot of paper. I thought I grabbed a chunk. Maybe not enough of a chunk. All right. I'm using this. The next one that I have is going to be my tangential at B. So my A tangential at B is going to be equal to, and here again, going back to my equation sheet, radius times the angular acceleration of link number 2. So it's going to be the radius to B times the angular acceleration of link number 2. So the radius to link B we know to be 3 inches, and the angular acceleration from what was given in our problem was 200 radians per second squared. Okay, 200 radians per second squared. And what's nice is it's in the correct units. Okay. So my tangential at B, no squares in this one. So it should be 600, right? And that's going to be inches per second squared. And then my last magnitude that I can calculate is going to be the normal at C relative to B. So the acceleration normal at C relative to B. This one, we have to use the velocity squared over radius because we didn't calculate the angular velocity of that link. So this is going to be the velocity of C relative to B squared divided by the radius of C to B, which is the length of link number 3. So the velocity of C relative to B, we measured from the vector diagram, 16.168. I'm sorry, 16.68. Square that divided by 10 inches, which is the length of link number 3. So I got 27.82 inches per second squared. So now we have those 4 magnitudes. We're ready to do the vector diagram to solve for our 2 unknowns. Okay. All right. So any questions right now? And I just want to confirm, I'm going to try to get these 4 quantities on the screen at the same time so that hopefully everybody has the same answers as me going forward. All right, now we're ready for our relative acceleration vector diagram. So this is what we are going to use. And remember, we want to start where we know the most, which is right here with our accelerations, normal and tangential at B. So let's go over to AutoCAD. Okay. Now these values, I'm looking 386, 740, 600. So I think I'm going to divide each one of them by 100. So just kind of looking at the perspective here. And I think I'm going to put it on this side over here. So I'm going to copy my origin here. And I'm going to go over here. We might have to move this around a little bit because I'm not exactly sure which way it's going to go. But we're going to put in place also the vector diagram. I want to have that on the screen so I don't have to go back and forth. Okay. I know this one is a lot longer, so we're going to increase that. So we're going to do the acceleration. You know, something I really don't like is the touchpad on my laptop. Do you guys use the touchpad on your laptop, like to maneuver around? Rarely, I know. And then especially in AutoCAD, if you accidentally hit it with your thumb, then it kind of does goofy things. So normal. So this is going to be the acceleration normal at C plus vectorially. It's going to take me a little bit to get this in place. Plus vectorially, the acceleration tangential at C. And then we're going to have the acceleration normal at B plus vectorially the acceleration tangential at B plus vectorially the acceleration normal at C relative to B. And then plus vectorially the acceleration tangential at C relative to B. Okay. All right. Again, just to have that available to us. So we know the most starting on the right-hand side. Let's see, I gotta do this one. It's gonna be B. There we go. We're gonna know the most right here. So we're gonna start with our acceleration normal at B. As we look back underneath and we use our equation sheet, we know that the normal components are always going to point from their point down towards their center of rotation. So along whatever link that they're on. So what that gives us the opportunity to do in CAD is I can simply copy, well, this one's pretty easy because it's a horizontal line. I can simply copy that link and point, and I'm going to put it at the origin right there. I'm going to change this to green, my object 2. And I need to now make this a length of the magnitude of that length. So the magnitude of the normal component at B is 740. So that means that my radius is going to be 7.401. 7.401. And then I'm going to extend to the end of that radius. Okay. Now I know that this is going from B towards my center of rotation. So that means the arrowhead is going to be going to the right. And this is going to be the acceleration normal at B. Okay. That's my first vector. My second one is going to be the tangential. Now the tangential we know is going to be perpendicular to that link in the direction of angular acceleration. So if we look back at the problem underneath here, it told us that this was accelerating. So it was speeding up. So that means that our angular acceleration is going in the same direction as rotation or motion. So that means it's also going to point down, okay, perpendicular to that link. So going back over here on the endpoint of B, because this was a horizontal link, this is going to have a line of action going straight down, and its magnitude for the tangential at B was 600. So this is going to be 6 inches long. Okay. And it will point down. I'm going to scale this down a little bit. Mine is just I think they're a little big. So this is going to be the tangential of B. Okay. There we go. Any questions so far? All right. So now we're going to go to the normal of C relative to B. So C relative to B is link number 3. As we look underneath at our equation sheet, our normal is always going to be pointing back to its center of rotation. Now, on a relative link, we are going to go from the unknown, which is the velocity of C, to B. So we're going to point to B. We're going to start our tail at C and we're going to point at B. So if we go here, it's C relative to B. So it's along that line. So I'm going to copy this link and I'm going to go to my endpoint here. The tail is going to start at the endpoint of my tangential. So I'm going to go endpoint here, make sure I grab that. And then it is going to point towards B. So it's going to go up and to the right. So I'm going to change this to object 3. And now I need to make it the correct length. The length that I calculated for the normal of C relative to B was 27.82. So I'm going to draw this at 0.27, right? Divide by 100, because this was 6. So I divided by 100. So I have to divide this by 100. So 0.2782 is going to be the length. So I'm going to go here, 0.2782. Enter. Oh, it's tiny. That's okay. So that's okay. Just make sure it's there. So I'm going to trim this one away here. That is the length of that vector right there. And we know that it's arrowhead. Oh my goodness. Yeah, get creative on this one. Might have to zoom in and do a screenshot just showing that one little one, but oopsie. There we go. Boy, how am I going to even label that? Well, it's down there. This is going to be the normal of C relative to B. All right, so we're going to have to zoom in and get that little difference. So I'm going to do a quick save here. All right, then that was my normal of C relative to B. Now I have to do the tangential. Now the tangential of C relative to B is going to be perpendicular to the line connecting those 2 points. So this line of action for our velocity of C relative to B is exactly the same. So I'm going to grab that endpoint and I'm just going to go and I'm going to put it on the very end of that little vector that we just added. Okay. And I'm going to label that one. I don't know which way it's going yet. We're going to have to find an intersection on the other side. This is the tangential. Okay. So it might go the other way. I don't know yet. We've got to do this side over here. So save. All right. Any questions so far, or does your diagram look the same as mine, hopefully, or very similar? Okay. So now we're going to work on our normal at C. So if we go back underneath, we were able to calculate the magnitude of the acceleration normal at C, and it was 387. So dividing by 100, it's going to be 3.869 or 3.8669. So go back over here. The direction of the normal component at C is going to be along this line. So remember, it's going to go from its point and point back to its center of rotation. So we're going to grab that line. It's along that line. And we're going to grab that. And we know that it is going to start at our origin right there. And I'm going to change its color so that we can see that it is that. Now, we know that its magnitude is 386.69. So I'm going to do a radius here of 3.8669. There we go. And I'm going to trim this end here. And then I'm going to change to my object layer and I'm going to put my arrowheads for this one right there. And I'm going to get rid of that radius. And this is going to be my normal acceleration at C. So again, the normal is always along the link going from the point pointing towards the center of rotation. So that's why we know it's going down and to the right. And then the acceleration tangential at C is going to be perpendicular to that link, okay? And it's going to go in the direction of acceleration. So now what we're going to do is we're going to take the same line of action that the velocity at C was, and it'll be the same as the tangential. So it's right there. Good. We got an intersection. It's always good when we have an intersection. So I'm going to move this over, okay? And we're going to trim off the parts that we don't need here. And then we're going to add our arrowhead to the end of that intersection. So right here to here, because we're adding this vector. So its tail is going to be at the end point of the normal, and its tip is going to be at the intersection that we just created. And then this is going to be our tangential. Let's see. All right. And then we're going to add the arrowheads here for the tangential C relative to B. Yeah. Now, if we look back at our problem statement, so I have these identified, but I want to know which ones I need to measure. So our original problem needs us to find the angular velocity of link number 4, right? Link number 4. So that means it's the angular velocity of this link right here. So if we look at, we have now our tangential and our normal. So you'll notice that angular acceleration is for the tangential component, right? So that means that to solve for the angular acceleration of link number 4, we're going to need the tangential component at C, right? Right? So let me go back over here. And I know that my angular acceleration of link number 4 is going to be equal to the acceleration of the tangential acceleration at C divided by the radius to C. That makes sense? So all I did was I rearranged this equation to solve for the angular acceleration. So the angular acceleration of 4 is going to be the tangential at C divided by the radius. So this one we're going to measure. We're going to measure that on our vector diagram, okay? So the tangential, not the normal, the tangential. I'm going to do an aligned dimension, endpoint to endpoint. Change that to the notes layer so I can read it. And you'll notice here that it's 4.0475. So we need to move the decimal place 2 places to the right. So that means that our acceleration tangential at C is going to be 404.75. Okay. And that is going to be inches per second squared divided by the radius to point C from its center of rotation, which is 6 inches. Okay. So our acceleration then, angular acceleration of link number 4 is 404.75 divided by 6. Do you guys get 67.45? Close enough, okay. Now our inches cancel out top to bottom, so we have nothing per second squared or radians per second squared, right? Now, we're not quite done because we need to add a direction, clockwise or counterclockwise here, because this is a, this is a rotation. So if we look here back at our diagram, the acceleration of the tangential at C is going down and to the left. So that means when we go over to our link here, this is going to be going down and to the left. We also, and we don't have it marked here, but we also found out that the angular velocity is going to be going counterclockwise, and so will the acceleration. So that means it's speeding up, okay? Because the acceleration ends up being in the same direction as the angular velocity. So this is going to be counterclockwise. And that, if I remember correctly for this problem, we needed to find W4, okay? We need to find W4, which was the angular velocity of link number 4. And we found that after we did our relative velocity, and we found that to be 76.664 RPMs clockwise, or counterclockwise, I'm sorry. And then we needed to find our angular acceleration for that very same link. And that we just found to be 67.45 radians per second squared. You can leave it at that. You don't need to flip this over to revolutions, as we've talked about, and also add the direction, in this case, of counterclockwise. Okay. Now, as far as including items, you need to include any and all hand calculations that you did. Okay. So, you know, my knowns, my unknowns. I did this sketch so that we could do it. If you didn't do this sketch, that's okay, because you would have created a diagram in AutoCAD. But then your relative velocity equation with any calculations that you did, your W4, your angular velocity of that link, and then any calculations for the relative accelerations, and then the calculation for the angular acceleration. So all of these need to be included. And then additionally for this, you're going to need your original kinematic diagram with all your labels. You're going to need your velocity vector diagram with labels and the equation. And then you're also going to need, I'm going to move this one, I guess, down a little bit. You're going to need your acceleration vector diagram with the equation and all of the labels. And you don't need to dimension anything but what we needed. So in this case, we only needed the tangential component at C to calculate the angular velocity. I'm sorry, the angular acceleration of link number 4. So that's the only dimension I added on here. Okay. So make sure that you have all these. Now, again, you might have to do separate screenshots for each of these because the scaling probably won't allow you to get it all in one, because I want to be sure to be able to see everything. So as we go back to our PowerPoint and we look, this was, now again, we changed this from 735. We did 739, okay? And now you're ready to complete the homework assignments. So I'm going to stop the video here, and then we're going to do one more video just as an overview of the assignment, including the last problems that will apply to what we worked on today.